Mm. Recording fine, right? Yeah. Cool. Hopefully it's showing the right page. Does it look like PowerPoint to everyone else? No one's objecting. There we go. Thumbs up. Yeah. So I'm going to talk about Nowcasting the 2022 Mpox outbreak. Apparently, so Sam asked me last week what if this was what I was going to talk about. I sent him a different title and a different abstract, and he sent this one through in the email to everyone. So this is the one you're getting. But this is all right because this is the one that makes sense, and this is the one that Sam and I discussed many months ago, and then I forgot because I've been on paternity leave and my life has been confusing. So I would talk much about what Mpox was. So, 2022 we saw this big global outbreak. So everyone's kind of aware of it. And what we saw was the public health agencies, the UKHSA, one of them, I'm sure many others, would release their incidence curves, and they like to do this by date of symptom onset. So here is a snapshot from the first technical briefing published in the UK of the number of Mpox cases by date of symptom onset up to, I guess, the 3rd of June, was the last, but this was published on the 8th of June. And what we can see here is we see something that looks like a really nice traditional epi curve. It's gone up, it's peaked at some point in May, and it's come down. The epidemic's over. Everyone can celebrate and go home. The only thing that means that's not the case is this dashed line here. And I've not added the caveat, but in the report, it says ignore everything to the right side of this dashed line because of backfilling and lag reporting. Now, this being an Epi Nowcast community seminar, I doubt this is shock to anyone that Epi data are subject to substantial lags, and we see a lot of backfilling, and then we get this type of behaviour with the epidemic curve. But for non-specialists, it's not always clear, and people could look at this curve and be like, well, what's the fuss about? Why are we worrying? And it's fine just to put this dashed line on with a caveat. I'd prefer just to put the dashed line on and bin everything on the right-hand side because it's so uninformative, it leads to misleading interpretations, but that's not my call. But, so it's fine to just present it like this, but as mathematicians and statisticians, can we do something better? Can we use our models to try and work out what the data should look like? The answer is yes, and the solution is nowcasting. I could end the talk here, I guess, because you all know a lot about it, but I'll talk you through the details of what we did in UKHSA. The first question you might all have is why didn't we just use Epi Nowcast? Wonderful package for developing nowcasting models. And we tried. I spoke to Sam, I scoped out whether it would be a suitable package. Then we tried to implement it and then realized that the permissions required for the secure laptops we were using to manage the data wouldn't let us install anything STAN or RTools related, so we couldn't really use any custom packages for any of these types of projects. So we had to go back to basics and basically make a model that would work with standard R packages that we could get installed. Spoiler is we succeeded, and the results are shown here. So this is pretty much the same time frame as this first plot here. The red dots are how the data appeared in real time. The blue dots are where the data ended up when we looked back a few months later. And the grey region is what the nowcast was happening. So we'll now go into math land, which is why we've now got a nice black background for these slides. So why is nowcasting a problem? Well, if we picture the timeline of sort of different cases during an infectious disease outbreak. So this could be 2 different patients. So the first patient, they get infected before the second patient. After some random time delay, they develop symptoms. Then at some point, they decide to go get themselves tested. And then at some random time after that, that test result gets processed, makes its way through the data pipeline into our system. And this first person, so they've got really long time delays between all of their events. And the second person has really short time delays between all of their events. And if we assume that this dotted line is today in this mystical land, then this first person, we haven't seen this person in our data yet because they've not actually been reported to us. So okay, they've been infected, they've got symptoms, they've gone for a test, but we've no idea if they're positive, if they're negative. So we do not see this person in our data. The second person, although they're actually infected later than the first person, we happen to see them in our data. And the issue this causes is, as this white line moves forward in time, this person enters our data set, and then we backfill all of these historic events. And so if we're looking at the infection curve by symptom onset date, which is typical, we've got quite a long delay here from them developing symptoms to actually being reported that they have those symptoms. Ideally, we'd want to visualize the curve by infection date, but we rarely see that in practice. Yeah, and that's kind of what we're seeing here. So these are some high quality graphs that I generated. The yellow curve over here is what the observed incidence looks like, and we see during an epidemic it's growing, and then it starts to drop off towards the end of the time series as we get loads of missing data, whereas the true incidence could have still been growing exponentially. And what the aim of this nowcasting, we're trying to basically work out this green shaded region here. We want to backfill and work out where the actual incidence is. One solution is, instead of using symptom onset, we could just use reporting date that has no delay. But as you can see from this figure here, reporting date is substantially lagged relative to symptom onset date. And I think for Mpox, it was around up to a month. You maybe saw 50% missingness. So between symptom onset and reporting date. So it's taken a long time for these cases to get reported. And if you're trying to work out, whether a vaccination strategy is working and you're visualizing the epidemic curve by reporting date, you have no idea how the peak in reporting date corresponds to when you implemented vaccination or any other type of isolation strategy. And that's why we want to push these epidemiological events as far back as possible to get as close to the infection date as we can. So this is just a bit more of how it looked during Mpox. So a little plot down here in the bottom left. So the grey was the cases reported by the 26th of May, and then the different colours here are just as we're throwing in all of those backfill cases. So you can see, we're usually for the next 2 weeks, there's substantial amounts of backfilling going on in this data. There's a lot of missingness and a lot of cases that haven't been reported yet, and it really changes the shape of the epidemic curve from looking like it was peaking here to looking like it was peaking here, and that will keep growing. I think the peak was actually some point in late June, early July, so we're looking at another month and a half past this point of the epidemic was still growing, and it shows the importance of these methods to try to predict what the epidemic curve is actually doing. This plot on the right here is just the empirical data on what the time delay distribution looked like for Mpox. Forgive the terrible axis names, but it's just automatically generated from after it. But basically, we can see here, the mode was around 10 days it took for cases to be reported. The mean was somewhere around 15 to 20 days. But even at 30 days, around a month, you still have quite substantial density and multiple tail cases that have been cut off this plot. So we want to address that, and so we were tasked, can we come up with a nowcasting model to say what this epidemic curve is doing in real time? So now we can talk about reporting triangles, which we're probably all very familiar with, but I'll go through from scratch anyway. So for each individual in our data set, we can think of the observation as a pair of two events. So for individual I, the data is the date of the event that we're interested in. So it could be symptom onset date, it could be specimen date, whatever we're trying to nowcast. And then we have a second event, which is the date that that event has been reported. We can convert this to the date of the event and the reporting delay, so the difference between these two time points. They correspond to each other. And we can now aggregate all of these into a matrix of our data. So as we come down the matrix here, we're looking through epidemiological time. So we've got day 1 of the outbreak, day 2, day 3, day 4, day 5, day 6. And then as we move along this direction, we're looking at the reporting delay. So day 1 reporting day 0, the little a here is the number of events that occurred on day 1 and were reported on day 1. Then number of events that occurred on day 2 occurred on day 1, reported on day 2. And so on as we increase the reporting delay. And the key thing to note here is if we take the sum along each row of this matrix, that gives us the number of events that have occurred on. So if we sum up every possible reporting delay, that tells us how many events occurred on the given day of interest. So that's easy, right? We've got this matrix. Why don't we just take the sum of all of those rows and we've got the answer we're looking for? Well, why do we need to do any maths? Well, the challenging thing is that we're calling this a reporting triangle because most of this matrix, well, I guess just under most of this matrix is missing. In this case, it's slightly less than half. We don't know. So if day 6 is today, we know how many events occurred today and they're reported today. We have no idea how many events occurred today and were reported tomorrow and all the way into the future. So we need to predict this missing part of the matrix. And once we've predicted this missing part, then we can just take those rows and we can predict what we are trying to do. But there's some issues with the sound. Do you want me to speak louder or slower?
I think it's when you have your hand on your face or you're leaning forward or back, any position that isn't your current position, it seems a little bit less good. Yeah.
Cool. Right. So for anyone who's missed the first parts, we want to find this missing part of the matrix is what we're trying to do, basically. And the missing part is the future observations. So that's basically what I was saying here. So from our data, we basically get this equation here where the number of events that occur on day t, so yt, is equal to the sum of the number of events that occurred on day t and were reported after d days for every possible value of d, where d is this reporting delay. So this is just saying, yeah, the number of events on each day is that row sum from the matrix. So the expected value of the summed here on the right-hand side is equal to the number of events that occurred on day t times by the probability that they were reported after d days. And we're going to make an assumption that there's some vague exponential structure to the data, so because it's an epidemic. So we're going to assume that yt is equal to y0 times by e to s of t, where t is some smooth function of time. And then if we take log of both sides, we get the sort of log of our expected observations is something that looks a bit like an intercept, something that we can model as a spline, and then the log of our reporting delay distribution, PD. The reason we're doing all this is these are integer counts that are generated from a stochastic process, so we can model these as samples that are from a negative binomial distribution. Because we've got something that looks like a spline, we can naturally just use a generalized analytical model. We can just simply do an MGCV in R, which worked nicely on our sort of limited R configuration that we had on our laptops. And then we have a model that looks a bit like this. I've added a few extra terms. So on our left-hand side, we've got our log transformed data. So we've got a log link in our negative binomial model. We've got the intercept, which corresponds to whatever this y0 initial condition was. In practice, it doesn't really matter. It's just an intercept. The model will do with it whatever it wants. We then have a spline that captures this ST, so that captures the shape of the epidemic over time. We use penalized cubic regression splines in our model, but use whatever your favorite flavor of spline is. Then we have the logarithm of our reporting delay distribution, our log PD. And there's two approaches we could do to this. So if you just had the matrix of data, you could replace this log PD with another spline that runs on the reporting delay rather than the event time, and that would work fine. But because at UK today we had individual level patient data, we were able to look at the actual delay for every single patient. We can empirically estimate what the reporting delay distribution could look like, then take the log of that and add that into the model as an offset so that we're actually using the true reporting delay distribution that's been configured elsewhere rather than letting the model fit too many things at once. And then we add some random effects for the day of week of the event and the day of week that the event got reported, and then an error. So that's the general structure of the model. Now we're going to have a detour, which is where everyone loves seeing bits about time delays. So here I've said, well, we can just estimate this PD. Well, how do we go about estimating the reporting delay distribution from patient level data? So right truncation and epidemic phase bias are two of the key things we need to think about when we're doing that. So we have our data that gives us individual data on when the event occurs and when the event was reported. We could, but you can't just take that data and estimate it just by fitting a distribution, because those data suffer from right truncation because we don't see anything that's being reported in the future. And then that right truncation is subject to an epidemic phase bias, where during the growing phase of the epidemic, the right truncation is more severe, and during the decay phase of an epidemic, it has less impact, but also we care less about what the model's doing in the same decay phase of an epidemic because it's over and the public health response is winding down. So the reason we get right truncation is, so if we assume we've got an epidemic timeline going from day 0 to day T, if someone sort of has their event really early in the epidemic, this person will be reported regardless of how long that random reporting delay takes. Whereas if if their event happens near the end of the epidemic, we only observe them if they have a shorter than average time delay, and this biases the observed time delay to shorter than the true values. And this is exacerbated during the epidemic growth phase because most of your observations come from this phase near to time T. We also have an interval censoring bias. So these data just tell us the day that the event occurs. We don't know the exact second the event occurred. I mean, they could, if someone told me the exact second, I probably wouldn't trust them anyway. But we generally have days, or sometimes these intervals can be longer. During COVID, early days of COVID, everyone was looking at incubation periods based on travel in and out of Wuhan, which were giving interval censoring of up to a month in some cases. So, these intervals are quite long. And instead of just ignoring these data, why don't we develop some nice methods to correct for them? In our case, it was just daily censoring, but even daily censoring leads to an up to 48-hour variation in what a pattern of observations means, because it could be midnight one night and then first thing in the morning, or it could be first thing in the morning with the first event and then midnight for the second event, which basically, these data can be quite misleading if we don't adjust these biases appropriately. So for right truncation, there's 3 general approaches that we could take. So the first is, I like to think of it as a forward approach. So if we have S is our second event here and S is our first event, so that I don't get confused when I'm talking about this slide. So the forward approach is we say, well, what's the probability that we see the second event happen at time S, given that the first event happened at time F? And we also need to condition on the fact that our second event has to have occurred before our truncation time T. And if you expand this and then simplify it, you get a nice expression here where you just have the density function on the top and the cumulative distribution function on the bottom. You can have a backward approach, which is flipped. So you say, well, conditional on the fact that our second event happened at time S, what's the probability that the first event happened at time F? You can go through and solve this again. You get an equation that looks a bit more unpleasant on the right-hand side. And the key term to note here is these P, F equals F terms, and these are the shape of your epidemic curve. So it's basically you need to adjust for what your epidemic curve is doing over time to apply this backward method, whereas in the forward method, those epidemic curve terms cancel each other out. And there's also a joint approach where you say, okay, well, what's the probability that we see both the first event on F and the second event on S, conditional on S being less than T. And again, you get something that looks a bit grim with the epidemic phase terms in your right-hand side. I mean, they look a bit grim. They wouldn't be that hard to solve if we had any idea what the epidemic curve looked like. But if we knew exactly what the epidemic curve looked like, there would be no point in doing nowcasting in the first place. So generally, we have to make some assumptions and approximations about these anyway. So I prefer using the forward approach because we don't have to worry about what the epidemic curve is looking like, but the model does all of that for us. Interval censoring is relatively straightforward. Basically, instead of having equals here, we just say, okay, what's the probability that F is within an interval and F is within an interval. So these are all quite straightforward, but what happens when we want to couple these things together? We get something that looks a bit like this. So we want the probability that I changed letters here and I should have made these consistent. So the probability that our second event is between E1 and E2, given that the first event was between S1 and S2, and our second event is less than T. So you can expand it. And then what we do is we apply a latent variable approach. So we introduce random variables E star and S star that have uniform distributions over our observation window. And then if you do that and you go through the algebra of this forward approach, you basically end up with something really similar. On the right-hand side, you just have your density function on the top and your distribution function on the bottom, and you just need to integrate it over those uniform prior distributions that we've assumed on E star and S star. So now I've got here in orange that we should always ask where the assumption is, because here I've just written equals everywhere, but this is really a fabrication because there's an approximation in here, and this is where the approximation has come in. So we can't just apply a latent variable approach and get to this nice simple term. If we apply a latent variable to this, we end up with this expression here, where we get something nice and simple on the top of our model, but we still end up with an integral on the bottom of our model. And the assumption is that we've just made something akin to a midpoint approximation to this integral, where instead of a midpoint approximation, we've approximated it by the value evaluated at that latent variable. It generally seems to perform well. We're testing out some other methods. But really, this is very computation feasible, and it seems to work quite well. I think Sam might challenge me. I don't know if he's tested out any of the other methods, but we've got some ideas about whether we could try doing a proper midpoint approximation or summoned approximations for the integral and seeing how much of a difference it actually makes. But anyway, that's the type of model we want. And then here's the way I visualize to check if we're getting the correct time delay once we've done all of this modeling. So here in blue is the cumulative rolling average of samples in the data over time. So it starts off really noisy because we have very few observations. As you get more and more observations, it becomes smoother, but eventually it starts to basically curve down, and that's because we're seeing this truncation effect where, okay, we're adding more samples, we're getting more confident in our rolling average, but our rolling average is becoming biased because the samples we're adding are a lot shorter than they actually should be. And what we want the model to do is to pick out where the data were constant before this truncation sort of decay started. I mean, this is synthetic data, it works perfectly, but this is the type of visualization you can do to check you're getting your time delay accurate. Does your model average pick out something that looks like a sensible pattern in your actual rolling average of your data? But anyway, that's the end of the detail, right? We can come back to Nowcasting again. So the reason we do all of that is so that we can get a really reliable estimate for what the probability of the time delay being equal to D-day is, so that we can plug that into our model down here. So when we take the log of it and add it as an offset, we want it to be as reliable as possible. And that's why we want to make sure we're doing those good methods rather than just letting the model put splines to it. We all know that splines can be problematic at the best of times. So if you're adding multiple splines into your model, you're just asking for the danger. So we've done that, and we've seen these plots before, but generally the model seems to work quite well for our Mpox scenario. So got from before, as I said, we've got those red lines, red dots as the original data, the blue dots are the backfill data, and then the Nowcast in black generally seems to hit the data as we'd expect. And here's just another plot showing what happened over time. This was by specimen date rather than symptom onset date, ignore what it says on the x-axis. One thing that was quite interesting was, as the epidemic was well established, and there was a clear day of week cycle had entered into the specimen date data stream, and the model was able to capture that out really well. But early in the epidemic, so here the day of week cycle has maybe been established for just a week or so, the model really struggled to capture the amplitude of those day of week oscillations. I mean, that's what we'd expect because it doesn't have much data to work out what that pattern should look like. And it's reassuring to see that as we did add more data, that the model was able to actually pick up those day of week cycles rightly. But there were some complications, which I think would be quite interesting to discuss here. And these are complications about using these methods in real-time data. So the first thing that happened was during the outbreak, after the first month or so, they decided to completely change the procedure they were using for processing tests. And obviously this will mess up any Nowcasting model because we train the model on the historic reporting cycle. So if the reporting behavior suddenly changes with a step change, the model has no way of knowing what's going on. And so in the UK, what happened was the 30th of June, they decided to add an extra day for test turnaround time. I mean, it's basically the outbreak had been going on for a month or two. People needed a break, so they wanted to basically just slow down the process a little bit. And then a week later, they also decided to stop processing over the weekend, again for the same reason. And this had the added complication of it added an extra day to tests if they were still being processed on a Saturday, but tests that had been finished that would have already been processed by the Saturday, saw no change to their reporting delay. And basically, we noticed these from the model, we noticed these as soon as they happened in the data, because suddenly the model went from doing something that looked really sensible, continuing epidemic curve, to just dropping off a cliff, which we know from an epidemic, we're not expecting such a sudden step change. So being within UKHC, we were able to discuss this with the data curation team, and that basically highlighted that these changes had been made. So we were not aware of these. We noticed that the model was doing something weird, spoke to the people who were in charge of all of the data pipelines, and they basically told us that this policy had been introduced. And because we had that, we were able to know exactly what the policy was. We were able to discuss how we think the policy will affect the data, as I said, through the 1 extra day to all tests, and the 1 extra day to weekend test. And then since we knew how we were expecting the data to change, we could go into our historic data, we could modify it to reflect this new reporting cycle, train the model on the new reporting cycle that we basically made based on the historic data, and then run this forward for the predictions. And that seemed to work pretty well. Another complication then is in hidden reporting delays, which even if no one changes anything about test processing procedure, hidden reporting delays can easily be prevalent in nowcasting data, depending on the type of database design you've got. So the type of database we had is we just had a live feed from the database. So every day we could go in and take a look at it, but we were only running the model once or twice a week. We weren't taking snapshots of the database every single day, just because it's just extra work that we didn't want to do, and then we realized it would be an issue if it was already too late. But basically, if you haven't, an issue with that was we need to know the date that the event was reported, not the date that the case was reported. And so the symptom onset date, they're typically going to be the same thing, because the case will be created the same day that person goes and gets their test. So those data will exist at the same time. But for symptom onset date, what was happening was that we were finding about patients, we were creating a record for them in the database, and that creates their case reported date. And then after their case was generated, someone would contact the individual and give them a follow-up questionnaire and ask them about their symptoms. And this could easily take quite a few days after the case was initially reported. So the actual date that their symptom onset date was reported, date that their symptom onset date was reported to us was actually later than the date that the case was reported to us. But if you just look at the database and use the date of report, that isn't consistent with the date that the event was reported. So to address this, we did a small study where we just took a daily snapshot every day for 2 weeks to determine what the true reporting delay was. We compared it to the observed reporting delay, and we found that the mean difference between those two distributions was 2 days. Ideally, we do something fancy to modify the data to create the full shape of the distribution, but in practice, what we did is we just added 2 to every single reporting day in the data, so that it was more closely corresponding to the true reporting delay rather than the fake reporting delay that we saw in the data. And again, this then has led to substantially improved performance of the model. And we've done some model scoring. It was all done using scoring util package in R. If anyone's not used it, it's worth giving a go. And so there's a few things we were comparing here. Well, we scored all of these over the length of time being fitted and the number of lots used. I'm not showing all of those results. What I'm showing here is the comparison between the non-parametric model and the parametric model. So the non-parametric model is what happens if we just take a spline and fit that to the reporting delay, whereas the parametric model is that data-driven reporting delay where we fit it empirically using the right truncation corrected method and plug that in as an offset. And generally, we see that the parametric model is outperforming the non-parametric model, which is reassuring because it's a more painful model to run. And we also see that the data-driven modification model is outperforming the model with no modification. So the model with no modification is we take the raw reporting delay from the data, and we use that for our nowcasting. The data-driven one is we do those modifications to crowd by adding the extra days artificially to the reporting date. And by basically modifying the data in the way we believe the actual data generating process should be, it improves model performance. And I grayed out the onset dates here because after writing the paper, I realized that this made the data-driven model look worse than it should, because if you go back and look at the live database, there's no longer an issue from the fact that you've got these hidden reporting delays because they've all been backfilled. So it's an unfair comparison, and really this second row here should be performing considerably worse than it is in this example. And so it's nice to see that the data-driven model isn't doing worse than if we do nothing to the data. In the case when we don't need to do anything to the data. But in practice, the onset date model without the data-driven modification said that the epidemic peaked every single week, basically, because that 2 days was having such a substantial impact on the observed reporting. Cool, and that's just some scores, and then we can just look at some visualizations to see sort of how the model was doing qualitatively. So this is by symptom onset date, and I want you to view all of these as progress bars, is how I like to consider them. So if the bar is empty, then no data has been observed, and as the bar gets filled up, then more data gets observed. And this is looking at nowcasting predictions by different lead times. So lead time equals 0 days is the model trying to predict what's happening today. Lead time equals 8 days, trying to predict what happened 8 days ago. So unsurprisingly, the model does better at predicting what happened 8 days ago than it does today. And we can see that's because there's a lot more data, a lot more partial data has been reported 8 days ago than the partial data reported today. But generally, the model seems to capture the shape of the epidemic curve well, minus this blip at the start here. And the reason there's this blip at the start here is towards the end of June, they swapped the questionnaire from being someone rings you on the phone to someone sends you an email with a web link for you to fill out. And unsurprisingly, that massively cut the number of people that actually filled out the questionnaire. So the ascertainment rate of symptom onset information dropped from about 90% to below 50% within a 3-week period, which obviously made it look like the epidemic was declining. And then the model has gone and followed that decline and thinks it's also declining, and took a while before it realized it was not. So that's definitely somewhere we need to improve within the nowcasting space. Is how do we adjust for those time varying ascertainment rates of the data we're interested in without just attributing everything to the changing shape of the epidemic curve, which is not what we wanted to do. By specimen date, the model does a lot better than it does by symptom onset date, and the reason for this is the reporting delay is much shorter. So whereas here at 8 days we were under 30% complete, for specimen date by 8 days we were pretty much 100% complete. But the nice thing I like to highlight here is just how nice this day of week cycle looks in the model. And it's just always nice to see that the day of week random effect actually does what we want it to do from all perspective. And this is just an illustration of how it was used in practice. So we were running this every week for the incident management team at UK. And so we would give them what the epidemic curve looked like in the red data points. We'd plot the nowcast on top of that. And we would also work out the growth rate on both of these curves and compare the two. So if we look far away, the nowcast and the data growth rate are exactly the same, which is what we expect since the model is doing no nowcasting back here because all the data are complete. And then over the last few weeks, there's been sort of clear divergence between the data and the nowcast in terms of growth rate, with the nowcast painting a much more pessimistic picture than the data, but also a more accurate picture and hopefully more informative for the management. We also made a regional model. Not too much to shout out about here. People in the UK, we broke it down by how UK funding agencies view the country in terms of London and not London. But yeah, the main reason for doing this was just because as we can see, most of the cases were in London. By even aggregating everyone else, we've got much lower numbers. And that's the end.
Thanks, Chris. That was really great. I enjoyed the last little bit particularly. Does anyone have any questions? Seb, I assume this is a question about the funding split being sensible because all the best academics are in London.
Quite. Thank you very much, Chris. That was fascinating and great. And maybe you said it earlier, and it may have sort of I may have missed it or it got lost or something. But so at the end you talked about how you use the Nowcast for growth rate estimation and to correct for that. Was that the main application of that, or was there any other? I mean, you kind of said earlier, or they asked us to nowcast it, but do you know like what those results were then used for? Was it used to present the data in a different way, or mostly for those growth rate estimates, or something else?
Yeah, so it's mostly for direction and trend rather than values. So in terms of when I was evaluating model performance, my order of preference. I think my order of preference for scoring criteria was calibration, then bias, then interval score. And the reason for that is they didn't really care how wide the intervals were or like what the actual value was. They really cared about direction, which is why I preferred the bias, because I didn't want it to be, biased in one way or the other too much, because that's what, they're like, is it peaking? What's the probability of it peaking? They don't care what the actual value is and how precise that estimate is, because they don't do any planning on that. It's all about trend analysis. So that's why the growth rate was there, because then we could just give headline figures of doubling times if they want to be quick update. If that answers your question.
It does. It just raised another one. Can I? Well, I'm happy to let someone else ask another question first, and then I can come back.
No one else has that hand up, so
okay,
go for it.
Here I am. So you mentioned, I think that would be really interesting. You mentioned kind of, has it peaked or not? Would that be? Have you looked at that specifically? Because that's something where we're generally doing very poorly in any forecasting, because we don't. Well, often we don't have the right mechanisms in there, or generally it's really hard to predict. But I think it would be interesting to look specifically for nowcasting at whether a change in direction is correctly identified.
We didn't look at it, but definitely interesting.
Okay.
And it's definitely more feasible than in forecasting, right? Because you have that part. It's basically, the question is, are the partial data convincing, consistent with having peaked on?
Yeah. Okay.
And it usually gave more insights, but because around the peak there were lots of questions. But the issue was they kept changing data, and it was like you then be like, oh no, the model thinks it's peaked, and then oh no, they just changed how they pipeline the data again. Yeah.
Okay. Cool. Thank you.
Okay, I'm gonna go next.
Yeah,
Okay, so Chris, thank you for your presentation. My question is, what, if anything, would you have done differently, or what would you do differently the next time?
Good question.
Broadly speaking, assuming you have the same problem where you can't, say, run Bayesian analysis or something like that.
Yeah, I mean, so we didn't really start from scratch with this, because there was a package that people had written for doing actuarial forecasting that basically just used DLM now. But basically what we did is we just took the code from that, looked at it, and then turned it into a GAM instead. So that was a helpful starting point. It'd be nice to see what else is in the EPI literature. So all the EPI stuff I found was all Bayesian, it was all giant and stuff. But there could be something out there that's more suitable for frequency staff that computers seem happy with, but I didn't search too much just because I found this package. We use loads of GAMs in our work anyway, so it's easy enough just to switch this existing package into something we could use. So from that's already answering the question, but
okay, so that answered the method question, but is there anything you would have done differently in terms of how you structured your work or the timing, or was that mostly driven by the requests you were being given?
Yeah, it was mostly driven by, I mean, everything was wanted very quick answers. So we could have tried to work out how to get all permissions to use everything and all the Bayesian stuff. But that seemed to would have taken longer than just basically coding this up, which we were able to get in about a week, really. From an academic perspective, so in my Liverpool hat, in terms of the paper, it would have been really nice to compare these methods to the Bayesian methods and to see, what are the pros and cons of each method. Because retrospectively, we've been able to get all of the data out, so it all exists now on GitHub. We could use it as saved data. and run that type of analysis. And I think that would be nice from an academic publication point of view. But from a UKHSA perspective, then we'd have time to think about that. You know, we did the work, we wanted to get it published to sort of show what we were doing. But no one at UKHSA care if our model's slightly better or worse than someone else's. I mean, they might care, but compared to the amount of other work we've got to do, is it a good use of time? Probably not from a public health perspective, but would be a good academic project.
Right. Okay. Thanks. Sam, I think you were next. You want to go?
Yeah, I was going to say, Chris, do you want to pick your own questions rather than us controlling your ability to answer? Anyway, I just wanted to build on, Kelly actually asked my question, but my other question is, we as an organization don't have time for evaluation, blah, blah, blah. That is super common, right? All organizations that I've talked to, they all want to do evaluation, but they never actually do it. Which is totally understandable. What failure points would there be in your model that would make you want to do evaluation, or that you would really care about? Because like a 2 or 3% difference between method, who cares? Like, obviously fine. But say that one method incorrectly calls for outbreaks sporadically, but its average performance is fine. Like, that would be quite bad. Are there things there that you would want, that you would see in a new method, you would think, oh, that's a great feature, if that makes sense as a question?
Yeah, so one was numerical stability. So the non-parametric model, it's not obvious in this scoring table because I filtered out all the points where it did really crap, but some points would just shoot up to 10 trillion cases. And that was just the issue of having 2 splines. And and obviously not having enough model development time, I couldn't tune it to be numerically stable. And that's the advantage of having something that had more development time from an academic perspective, and you could trust the stability. That would be an important tool for public health, I think, because you want something you can trust. So even if the average performance was the same on those occasional weeks, right? I mean, you're always going to disregard it if it shoots up to over 1 million or whatever. But it's nice to have a model where you don't have to worry about that, and you can just press play, and it will deliver what you want it to do. Yeah, I guess the other thing would be weird, like, so if I looked at this, for example, where it's a dip at the start of July, if that wasn't explainable, that would be a concerning model feature, and I would have to look elsewhere to see what other types of models there were. So everywhere else, okay, like here it's overshooting a bit, but I'm not concerned because it picked up the downwards trend and things were coming down and people weren't too concerned at that point. But here was around the peak, the model was doing something stupid. And so in this case, I'm comfortable with it because I think every model would have done something stupid in this case. But yeah, that's the type of stuff that I'd be concerned with.
Caitlin, do you want to ask a question?
Sure. Thanks for a great talk, Chris. I just wanted to pick your brain a little bit about that point you made about that dip and that time varying ascertainment rate on the thing that you're trying to predict. I think this happens a lot, especially in early stages of an outbreak. And how do you think about the best ways to sort of incorporate those phase shifts in a model? And have you given any thought to, like, mathematically how we can do this?
No, I don't know. I mentioned it to Sam, and Sam said he had some ideas at one point. So I might pass it on to him. But I'm just trying to think in terms of in practice, it was just a caveat, just to say that it was being rubbish because of X, Y, Z. I think at UKHSA that's generally the thing we do when we know that there's a performance issue that we're unable to fix. It's best just to flag it because the stakeholders need the outputs because it's part of their usual information packs and whatever. So we need to deliver it, but we don't want them to deliver it and trust it. So we need to make it clear that we flag those issues. Either by say block shading in the background and saying ignore this period, or adding caveat bullet points. It's typically what we do, whether it's for forecasting or nowcasting. But yeah, definitely somewhere where we need more improvement.
And then in that instance, you knew about the change, so you were able to flag it.
Yeah, I've got the paper open. I can show what it looked like. See if I put that figure in the slides. Is it still sharing PowerPoint? Cool, I'll swap it over.
Yeah,
There's definitely a figure somewhere in this. I found on the thing. Cool. Yeah, so basically every time we ran the model, we visualized, we generated these plots, which were the ascertainment rate. So hopefully it's sharing word. So the left-hand plot is the ascertainment rate of specimen date, which was, it was noisy at the start, but there was nothing to really suggest to me it was changing substantially. But this is what happened with symptom onset date. So really early on, we were seeing close to 100% reporting of symptom onset date, because there were so few cases they were able to be tested by the health protection team who could ring them every day and ask them all these annoying questions. And then when it went to this online questionnaire at some point in June, yeah, that response rate just plummeted. So yeah, we were able to see in real time that that was going to be causing issues with the data, but unfortunately unable to do anything to actually correct them.
I have another question while we wait for other people to think about questions. So you were saying that if this happened again, kind of like, well, it will be the same. Can you now install Stan on your systems?
Well, it depends what we're doing. So we're doing some nowcasting for norovirus at the moment, which is using our normal computers, which we can't install Stan on. So we have been comparing every nowcast to this model and playing about with both of them. Not anywhere near final results yet. It's still experimental phase. But it really depends. So like the Mpox, because it was a response, you could only get data through a certain warehouse that was very, very carefully managed, and they would only send you certain laptops to run it on. So we couldn't use our regular IT infrastructure. So for now, most of our models that we do use are in Stan, because most of our work is done in AWS, where we can install whatever we want. But all of these had to be closed and done locally using a local studios.
Yeah,
But
that makes sense.
depends on who's in charge of cybersecurity for the outbreak, really, and what the policies will be.
Yeah.
Very, I think Mpox was just very sensitive. You know, but it's a sensitive topic, and a lot of concerns about data breaches and things like that.
Yeah, that makes sense. And just a final question. The delays, the weird database delays that were untracked, is that now been resolved, or is that like going to be a persistent problem, do you think?
They're just live databases, so and we don't, you know, we can just go in and get read access, I guess, or whatever, so we can go in and pull our data. So we could go in and pull data every day, but that's a bit of a crap task to assign someone. So it'd be nice to find some, you know, robust methods for correcting for that. Will be a nice bit of research.
That makes sense. I've heard that's what contracts are for. Cool. Does anyone else have any questions, or shall we wrap up?
I've not seen the chat, but is there anything?
I saw Kelly had a question earlier, but I'm not sure if it got answered.
So Dave Week effect, yeah. So that said Dave Week. Oh well, there's one about Dave Week effect in the chat, and that was because the plot said symptom onset date, but it was actually specimen date. Yeah, there are some Dave Week effects in onset date, and it's usually because people don't want to acknowledge their symptoms at the weekend and things like that. But yeah, the specimen date and where we see those really good.
Oh, there was a question about if you could share the GitHub again.
Yeah. Yeah, 1 second.
Is it in the paper?
Yeah, it should. Yes, yeah, it's in the paper, but I can drop the link in here.
All right. Any final questions?